Okay, and we are go. Okay, we're continuing with chapter 10.
We're now going over all more questions.
Fine, one more. Do we have both 8 and 9 or 8?
8 was due last. 8 was done, so it's now.
You guys should be paying attention. Which one?
Number 1.
And does anyone know where Simon is? What? Yeah, what's one?
Show you that I'm here.
What?
Consider.
Right.
Who's that? Who's that?
At least you heard it, right?
No, Simon is
Right.
not here.
You just replied.
What's question 1?
Consider the 3 points 1, 1, 4, 0, and 0, 8. If y equals a plus bx, set up an equation for how well this line fits the 3 points.
Oh, so that's just the fitness
The
thing.
fitness, yeah.
So that's basically going to be what it is. Remember, you have a, b is equal to, what was that formula for fitness?
A plus bx
minus y.
squared
A plus b x
Minus-
1 minus y 1,
y1.
right?
in parentheses squared plus
A
bx 2 minus y 2 squared plus a plus bx minus y 3 squared. Right, so this is just x1, y1, x2, y2, x3, y3. Basically just plug them in here. So that's just going to be
A plus b
a plus
minus 1
b minus 1
squared. A plus 4b squared. A plus a minus 8.
a minus 8 squared. That's it, that's the fitness. And basically the line of best fit is the line for which you can choose A and B so that this is as small as possible. Was that the only question? Or was that part A of the question?
That was part A.
no, that was it.
That was
That was it. And then the
Okay.
next question, they put it as 1, but I think it was supposed to be 2. No, no,
There's part A and part B.
It was part B too.
Yeah, so what does part B say?
The line goes through 4, 0, and 0, 8.
Wait, what? That's not.
And no, and then y equals 5. It's 2 different things, and then they want you to say, determine which of the following lines has the best fit for the 3 points that they gave you originally.
Okay, alright. So one was a line through this and the other was a what?
Y equals 5.7 minus 1.6x.
Okay, so let's look at 1. First of all, we have to find the equation of the line that does that,
Yeah.
which would be what?
Y equals 8 minus 2x.
Y equals 8 minus 2x. Right, so you do like the slope formula, y2 minus y1 equals x2 minus x1, and you do the y-intercept, and hopefully you get this. So if my x is 4, my y value would be 0, and if my x value is 0, my y value would be 8, so this is the line. So basically this says that a is 8 and b is minus 2. So what you're going to do is you're going to plug that into the fitness equation that you got from this part. So you're going to find 8 minus 2 of that function. You're going to have 8 minus 2 minus 1 squared plus 8 plus 4 times minus 2 squared plus 8 minus 8 squared. And that gave you what?
$25.
25?
Yes,
Exactly.
I think so. Yeah.
Okay. And so then you do the other one. So here you set A equals 5.7 and B equals minus 1.6. And you plug those into that equation again. So you have f of 5.7 comma minus 1.6. That'll be 5.7 minus 1.6 minus 1 squared plus 5.7 plus 4 times minus 1.6 squared plus 5.7 minus 8 squared. And what is that?
15.39.
15.3?
9.
Yeah.
Right, so line 2 has a better fit
And it's because it's smaller.
because because it's smaller.
So the smaller the number, the better
Yeah.
the fit?
The fit is, remember, it's kind of we're measuring the average distance between all the points. So if the average distance is smaller, then it better fits all the points.
Okay.
Yeah. Other questions?
Number 16.
Yeah.
It says
Can I have the text again?
they give you a chart.
Okay. All right, so we have SAT scores, which is X. And then we have the percentage of seniors taking it, with SAT scores is Y. Percentage of seniors taking exam is X. So we know that the mean of Y is 948. Mean of X is 35.7%. Standard deviation of Y is 66. Standard deviation of X is 27. It's an Excel problem.
Yeah.
No.
No, it's not.
No, it's not.
It's a regular.
It talks about Excel, but it's
Yeah.
not.
Go get it
Okay,
posted.
the file, blah, 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 presents whatever. Some sort of pretend table. Okay, the equation for the regression line is, so they told us the regression line, it's y equals minus 2.2 x plus 10.4. As the percentage of students taking the test increases, what happens to the average SAT scores? So A, as the percentage of takers increase, right? This means we have y equals minus 2.2x plus 1024, and x gets larger. What's going to happen to y? Huh? Y gets smaller
Oh, yeah.
because you're subtracting. Right, so the bigger this gets, the larger the number you're subtracting gets, and so it will fall.
Decreases.
So average SAT scores would fall. Yeah, just by using that equation. E. What average SAT score would you predict if 50% of of high school seniors took the exam? You just plug it in. So y would be minus 2.2 times 50 plus 1024.
914.
So this is the expected average score. What is the value of the correlation coefficient? So this is C. It's asking what is R here. How do you find that?
Use that
What is
formula,
R?
B equals R times.
Right, we know B equals R times SY over SX,
Yeah.
which means that R is equal to B times SX over SY. And then you just plug them in. The B is the coefficient of X, which is minus 2.2. SX was given in the table, that's 27. SY is 66. So that's roughly what? Negative? 0.9? Strong negative correlation.
Mhm.
Okay, so suppose the state had a 50% participation rate and the scores were average 1,000. Give a statistical explanation why this should be considered an extremely good result. It's an extremely good result because we expect it to be 914.
So that's enough of explanation?
Yeah.
Okay.
So the average score of 1,000 is a good result, since the expected score is 914, and there's a very strong correlation, right? It's like 0.9, that's close to 1, which means your regression line fits the point very closely, right? So for something to deviate from that, that's it. And to deviate in the positive way, it's actually a good score. So that would be enough, strong correlation. Other questions?
For 6B, we're using that equation, but I don't think they gave us the standard deviation of x.
6B.
Oh, I did
Yeah.
it for no reason. I think when I was doing it, like, you know when you're supposed to skip over? I forgot to skip over. Never mind.
You had something to do with it, didn't you? You look guilty.
I'm glad you see this.
Yeah, can you tell me where cyan is? Okay, other questions?
Do you want to go
What's in C?
15C. Can you find the equation of the regression line of height on weight from the information in parts A and B? If not, can you find the slope of this line? Well, technically, yeah. You just redo everything and switch the variables. Because they ask you to set up y versus x. This is really asking, can you set up x versus y? Well, you can use the same data and just do everything in the opposite way.
Yeah.
Can you roll to the right?
Okay, so the 3 points, 1, 3, da da da, line, a straight line. Find the equation of this line, then verify the formula is 9.1. Theorem 9.1. Okay, so you just find the equation of that line, which you just connect 2 points and find the equation. And then it's plug and chug with 9.1. And also 9.2. Where's theorem 9.2?
I may have worked it out. If it's not in
You may have ripped it out.
it. Like, sometimes, because it's such a heavy textbook, and I only carry it around, so I just take out pages.
What?
Does nobody else do that? I don't do that.
I think they think you're saying like you take out pages to make it later. She's saying
No,
like the
no,
pages she needs.
like the pages I'm gonna read during the day, you could just rip them out, you know?
Either way.
Yeah, 3. Don't worry about 3. It's really just plug and chug anyway. Once you find the equation of the line, your y-intercept is the a value, your slope is the b value, and you're pretty much plugging in the formulas into this thing, into the theorem and checking it. And then plug into whatever 9.2 is.
Are you talking one Oh. Yeah.
Yeah, so it's just plug and chug.
Yes.
After you find that equation, you take the slope to be the b and the y-intercept to be the a. It's just plugging in and chugging the equation. Other questions? Okay, you can pass the homework up.
So quiz is next Tuesday?
Monday?
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 We have class on Tuesday?
Wait, what happened? No school Monday?
Next Tuesday is a Monday schedule, so you have to come.
No.
So we don't see you on Monday? Wait, what?
He's making fun of me.
I don't lie.
Damn.
Besides, I gave you all the calendar, so you should know when what happens. Okay, so finally continuing with chapter 10.
Let's go over the fun probability.
So remember the Monty Hall problem, right?
Yeah.
Yeah. What?
The Monty Hall problem.
There's 21.
Oh, right, the goat.
The goat. Alba wants the goat, but everyone else wants the car, and that's
Oh wait,
fine.
whose homework did I take back?
So another way to think about this, if you didn't go through and map out all the situations, which is one method, one way you can think about it is, let's say you actually picked this door, right? What are the chances that the car is behind that door?
33%.
Right, 1 out of 3 chances. Which means what? What's the percentage? What's the chances that it's behind this door?
2/3.
So there would be 2 out of 3 chances for the car over here. It's just another way to think about the problem. It's good to do it multiple ways. Now what happens if he opens this door and then there's the goat?
That's a good.
Right? What does that actually mean? Well, you know there's a 1/3 chance the car is here. There was a 2/3 chance it was over here, but you know now definitely that it's not here. So what does that mean? The 2/3 chance gets concentrated only on that door, right? Because now this is not in play anymore, right? So originally when you made that choice, things really didn't change even though it apparently did so. But by showing you this, the probability gets concentrated on that. And there have been many puzzles since the Monty Hall problem where they sort of extend this idea. What if there were 100 doors? Right? Lots of doors. Right? And you pick one of them. Right? What are the chances that you get the car?
1 out of 100.
1 out of 100 chance to get the car. Which means, what is the chance that the car is somewhere else? 99% chance it's somewhere else. There's a 99% chance that you're wrong, right? Now what if Monty goes and he opens 98 of these doors?
Switch.
And there's only one door that's left not open.
Switch.
Now it kind of makes sense that, yeah, I should switch, because there's like a 99% chance I'm wrong, right? It turns out when you sort of make the scale smaller, the intuition sort of goes away because these numbers are kind of close together. It's sort of, right? But in a bigger sense, you realize that it makes a lot of sense to switch, right?
Yeah.
So sometimes that's another thing you can do. Think about the same kind of problem in a different context. Sometimes it will give you a strategy to use, right? It makes sense to switch in this situation. The strategy shouldn't change in a smaller situation, right? I could give you 1,000,000 doors and it's going to be the same strategy. Switching is actually the best strategy. Right?
Are you going to go over the Trojan example?
Sure. So, Freud, yes, we have to go back to Freud. So the next example was, a couple has 2 children. And so, what did I ask?
Possibility that both are girls was the first one.
So you have the
Yes.
couple has 2 children.
Hey.
What are the chances that both are girls?
Right, what is the probability both are girls? B.
If you know that one girl,
If
the
one is a girl, what's the probability that the other one is a girl? And C, if the older is a girl named Sienna, Florida. What is the probability that the other is a girl? See, this is why you shouldn't start because then I pick on them. Right? Now, at face value, this sort of seems like you're really kind of asking the same thing over and over. We're still asking if they're two girls, basically, right? Actually not. The questions are very different, and they all actually have a very different answer, right? So, can someone tell me how to think about it? Not Irving.
I solved it.
No, I talked to you about it after the class as well. So
Yeah, you just proved me
you
right.
have been influenced.
I have not.
Someone else give me a strategy for.
Wait, he knew the answer?
Me
I've
spoke about
done
the
this in
format.
genetics.
Someone else, give me
You
a
gotta
shot.
do
How would you
this.
figure out A? What is the probability that both are girls? How would
Can
you
I
think?
go on?
Yeah.
Oh, so I just put down like all the chances of the children. So
All the
that-
chances.
Yeah, like you can have a boy, girl,
Independent events.
girl,
You
boy.
wrote down all the possible
All the
situations,
possibilities, yeah,
right?
exactly.
So that's where you'd start. Possible situations,
Yeah,
right? Because remember, our probability was the number of ways something can happen divided by
Yeah.
all possible situations. So
Yeah.
it's a good place to start at all possible situations. So you can have a boy,
boy,
boy, girl,
girl, boy,
girl, boy,
girl.
girl, girl. Right? Okay, so how did you go
So
about it?
then for the first part that says what is the probability that both are girls, there's only one outcome where you have a girl
Right.
and a girl.
There's one outcome where there are two girls.
So
One
it's
outcome
One out of four.
for, let's say, A, probably of A.
Yeah.
And then there are a total of 4 total possibilities.
You could also just multiply.
Right, so probability of A is equal to just 1 out of 4. There's a 25% chance that both are girls. Okay, how would you think about B?
And then B says if you know that one is a girl, so you can automatically eliminate the boy option.
Right, so we have boy, boy, you know that boy, girl, and girl, boy, and girl, girl, right? So,
But one is a girl, so it'll automatically eliminate the boy option.
right, so in the B situation, this is no longer a possible
Yeah.
answer, because we know that at least one is a girl. So now there are actually 3 total possibilities.
And you have 1 out of 3.
And only one of them is a girl. So the probability in this case of 2 girls is actually 1 out of 3, completely different from the previous answer. Part C.
And then part C is if the older one is a girl, so there are only 2 options where the first child is a girl. So
The name doesn't matter, by the way,
Yeah.
if anyone was wondering. What is it out in Florida?
That threw me off.
So if you have boy, 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 girl, girl, boy, girl, girl. Right, so we know that the older one is a girl, right?
Yeah.
Which means the first position must be a G.
Yeah,
Which means this is no longer a possibility. Now there are only 2 possibilities.
so it's not happening.
And there's only one of them in which both are girls. So the probability of having 2 girls in this case is 1 out of 2, right? 3 problems that seem very similar, but they're actually very different, right? And it's all a matter of looking at chances. And you really want to come up with the thing is, what I'm trying to get at is, you don't want to sort of use your intuition at these things, because the language can sort of cloud the issue. You really want to come up with a systematic way of doing something. Do a diagram, do a table. You really want to do something that you can really see what all possible combinations, all total possibilities are, and then you sort of pick out the ones that you actually want. Right? And there are tons of probability puzzles. If you're interested, you can Google some and play around with them and get used to the idea of thinking in this way. So that was the solution to the couple having 2 girls problem.
Can we do more?
Probably a nice problem to think about. I don't remember what it is, but it's sort of it's like a 3 prisoners problem or something like that. when you have 3 people on death row or something like that, and one of them will be pardoned. I think you should look that up. 3 prisoners problem. It's like one or two of them are going to be pardoned, and you're one of the prisoners, and you want to try to figure out what are the chances you're going to be beheaded the next day. Yeah, it's a really interesting problem. But let's move on. Yeah, so as we mentioned before, probability is about looking at the chances of things. And as I said, originally this whole thing sort of developed out of gambling, right? People wanted to know what are their chances of beating a certain game, you know, how much money should they risk on something. But later on we found that it's really applicable to a lot of things, and it's inextricably linked to statistics. And you know, probably statistics gets a bad rap from people a lot of the time. But as far as, you know, those questions students all ask, how am I going to use this in my life? Probably statistics is pretty much the most applicable topics in math, in your life in general. There are so many things that this controls in your life, you'll be amazed, right? How much you pay for your car insurance, it's probably a statistics problem. This is how they figure out how much to charge you. Oh, you're between 18 and 24 male with a red Lamborghini? I know what to charge you for insurance. Why? Because they looked at all these statistics and they looked at all the chances. What are the chances of a male between 18 and 24 crashing a red Lamborghini costing us a lot of money? They looked this up, and based on that, they can tell you how much they're going to charge you, how much you pay for your mortgage, how long you're going to live, how many kids you're going to have, what your career is going to be, how likely are you going to use your major in your everyday life. These are all problems of statistics and probability. You might not see it, but it's there. And those people who are making the rules and charging you money for stuff, this is what they're using to determine how much to charge you. It's really like everywhere, right? So if you want to talk about how math affects your life, probably the statistics is where it's at, right? So it's some really important stuff. And I know we're going to be talking about problems like, oh, what if you flip a coin 6 times and blah, blah, blah. It's going to be like, how does this help me in my life? I know. The point is, learning how to think through these problems will help you to think of more real-world situations. So we want to sort of figure out how to think about things so that when it comes down to it and we are faced with a real situation, we can actually figure out the best strategy to get something done. One thing you'll notice here is that because we're counting total possibilities and counting how many ways something that we want to happen can happen, counting is obviously important, right? Being able to count something efficiently. Right? So if you're looking at statistics, remember a lot of times we're dealing with thousands of data points, hundreds of thousands of data points, millions of data points. You can't go through and be counting stuff like that. You want an efficient way to count stuff, right? So counting is a major topic in probability and statistics. There are entire math classes on nothing but counting called combinatorics. It's just a math class that teaches you how to count things efficiently. Right? We're going to use some of those principles from such a class. But yeah. From the definition of probability, we see counting is important. So are other tools, and we'll be doing a lot more of this as time goes on. Like drawing diagrams and tables, right, to help us figure out all the situations that we can possibly have, and then we can use them. So now let's talk about some counting rules. So there's a rule called the multiplication rule. So it says, if in a multi-staged experiment, and think of experiment in a very large context. It doesn't mean you're in a lab coat watching a titration video. It's a very general. right? Some event that is unfolding in front of you. We call it an experiment. And let's say it has multiple stages. Right? So there's a multi-stage experiment. There are n options or possibilities, n possible outcomes for the first stage. What notation do I use? N possible for the second stage. P possible for the third stage, etc. Then the total possibilities of outcomes for the entire experiment is just the multiplication of all possibilities of each stage. You multiply all of them. Example. Simple. How many outfits can you assemble?
Two different what?
Colored shirts, two different pants. Pants aren't important. Pants are optional. Right? How many possible outfits can you make? You have 3 different shirts, 2 different pants.
So it's 1/3 to the power.
It's 6 because it's 6.
So it's just 3 times 2.
Oh, come on.
6 possible outfits. Right? The experiment is putting your clothes on. It has 2 stages. You put on a shirt and you put on a pants. The first stage has 3 possibilities. The second stage has 2 possibilities. The total number of outfits you can make is 6. Right? So you don't want to spend time there, put that shirt and that pants and then put another shirt and that pants. No, you multiply them. Right? This is called the multiplication rule. Right? Gets us to count things a lot faster when we know that there's one experiment where it can be broken up into stages, and you know possibilities for each stage. You just multiply all these possibilities. That's the total number of outcomes. Right? So remember, I didn't ask for a probability, so you shouldn't be dividing anything. You're just I just asked for the total number of things. Right? You only divide with probabilities. Okay. So here's another example. The coin is tossed 3 times. How many outcomes are possible?
3, 6.
Think about it. B.
2. There's only 2 problems every time.
What is the probability?
Oh, very good. I'm so stupid.
of getting 3 heads. How many total possibilities are there?
There's 2.
Nope.
6.
Are you randomly guessing?
1 over 2 times 3, yeah. 1 over line. Don't
So you
Just do head. What is the question?
This is the question. It's right here.
have
You toss a coin 3 times. Flip it, boom. Flip it again, boom. Flip it again, boom. How many outcomes are possible?
3.
No.
6.
How do you get 6?
Say yes or say no.
there's
It's
6.
the right
No,
answer.
it's not 6.
No.
It's 9.
No, I got you right now.
Oh, is it 3
So-
factorial?
You gotta do what you were doing before. Head, tails. Head, tails, head. You know what I'm saying, right? Like what you were doing. Yeah, I know what I'm saying.
Where is that?
Head, tails,
What are
head,
you
tails,
talking
head. Tails, head, tails.
What is he? Can someone tell me what he's talking about?
You know what I'm saying? Just write it out and it will fall into place.
There's only 2 different.
So, there are a couple ways you can do it. You can do it by diagram. What are some possible situations? Well, I can flip and get 3 heads.
Oh, that's what you mean.
Or, I can get a head on the first one.
Tails.
Let's actually fill this out systematically.
Yeah.
Okay.
Whenever there's something that you can have 2 options, because when you flip a coin, there's head and tails. How you want to get all possibilities is you start 1 and you alternate. Tell you how many times you can alternate. And then the next one you alternate every 2.
How did you know that that's how many times we can alternate?
I will show you in the next one. So then you alternate every 4. That's actually all possibilities. Now, before I tell you the second way, you might just do this by trial and error to see what's missing. Right? I get 3 heads, I can get 2 heads and then a tail, or I can get a tail in the middle and 2 heads out here, or I can get a head and 2 tails. And you go through all the possibilities. These would be all possibilities, right? How many are there? 8 possibilities.
Explain.
Okay, so now, let's say you flip the coin 100 times. How many possibilities? You want to do this? Not really. So there's another way you can think about this. That you can get to that 8. Think of it as a multi-stage experiment. What are the stages?
Oh. Is it the thing where you like take the possible outcomes and do like 2 cubed, so it gives you 8?
Let's build it up. Think simple. What are the stages in this experiment?
Flipping a coin.
The flip.
Yeah.
A flip is a stage, right?
There's 3.
There's 1 flip. There's 2 flips. There's 3 flips. Each flip is a stage. That's how you start to think about it. Okay? So then we think, okay, there are 3 stages to this experiment. There's stage 1, which is the first flip. There's stage 2, which is the second flip. And there's stage 3, which is the third flip. Now, in the first stage, how many options are there? 2. You either get heads or tails. What about the second?
2.
Same thing. Third, same thing. So I have a 3-stage experiment where the possibilities at each stage is 2. Multiplication rule. So there are 8 possibilities. Okay, now answer part B. What is the probability that I get 3 heads?
1-8.
1/8. I know there are 8 possibilities. There's literally only one way to get 3 heads, by tossing 3 times. There's one way to get 3 heads out of 8 total possible outcomes. Probability of getting 3 heads is equal to 1 out of 8. So it's a matter of thinking, you know, you're given a word problem, you really want to break it down in your head as something that you can fit a definition to. So if you're using try to think of, is it an experiment? Is there stages somehow? Can I fit those in? And you can use something like a diagram or something a bit more sophisticated, like thinking of it in terms of stages to get to an answer. Diagrams can be tricky because you'll never know if you fulfill all possibilities unless you're actually looking at some other way to do it. But it can still get you there. Let's see. Oh, I had a note here to also do a tree diagram because sometimes they ask me for that. There's something called a tree diagram. Let me show you how that looks. If you have a relatively small number of things happening, you can do these guys. It really they get big really fast, so you probably don't want to do it if there are a lot of stuff to worry about, right? But in a tree diagram, what happens is you start at a point and you start to branch off with each possibility, right? So again, you do stages. So this is first flip, second flip, third flip. Now what you do is you start at a point and then you branch off for each possibility, right? So when you do the first flip, what are your options? You can either get an H or a T, right? Now on the second flip, what happens? If you got a heads first, that branches off, right? And then on the second flip, you can get a head or a tail. Now if you got a head or a tail, you can again branch off into a head or a tail. And then down here, you can get a head or a tail. Here you can get a head or a tail. Here you can get a head or a tail. Here you can get a head or a tail. Now the number of things at the end stage, that's the total number of possibilities. But this really brings you through all situations, right? There's one possibility of getting a head, then a head, then a head, head, then a tail, then a tail, head, then a tail, then a head, head, then a head, then a tail, right? Tail, then a head, then a head, tail, then a head, then a tail, tail, then a tail, then a head, tail, then a tail, then a tail. Right? Each arm, every time you run along one of these arms, it gives you one possible scenario happening, right? And ultimately, at the end, the tree will give you all possibilities happening. So this is called a tree diagram. It's a useful diagram to use when you can see things branching off. If there's something I neglected to mention, let's make sure. I probably should have mentioned this before the boy-girl example, but we made it through okay, so I'll mention it now. This is the equal likelihood that the definition, if you have n distinct elementary outcomes. Elementary just means basic, fundamental, single stage outcomes. And each is assumed to be equally likely. Then the probability of any one event probability is 1 out of n. If k outcomes favorable to an event A, then the probability of A is k over n. Now implicitly we actually use this here with the coin flips, right? We're assuming that we're equally likely to get a heads or a tails, so that's where we get the probability of this is 1 out of 2, right? It's basically using the equal likelihood principle. Okay, let's do another problem. Try to think. Try to get used to thinking in terms of probabilities. We toss 2 fair dice. If you distinguish between them, how many outcomes are possible? B. What's the probability that sum of the shown faces is 15? So we're going to be using the equal likelihood principle here. C. If you were to wager what the sum would be, what would you bet? Right, so if you're forced to put money on this game and they say pick a number that you think the sum of the faces are going to add up to, what number should you pick? Good. Okay, so let's think about this. I think.
That's the 36.
Where did you get that?
6 times 6.
Where did you get that?
Yeah, 6 spaces on the back.
Alright, so you toss up 2 fair dice. We're assuming all outcomes are equally likely, right? That's what the fair dice means. So for each dice, there are 6 possible outcomes. You can think of the dice in this sense as the stages. There are 2 stages. One stage has 6 possible outcomes. That's one dice. The other one has 6 possible outcomes. So there are 6 times 6 possible multiplication. Right? So die 1, there are 6 choices. Die 2, there are also 6 choices. That means there are 36 total possibilities. Okay? What is the probability that the sum of the shown faces is 15? Zero. 15. It should be 5, but yes, with 15 it would be 0. There's no way that you can get the 2 dice to add up to 15. I meant 5.
Is it 2 out of 26?
Is it? And remember, we're distinguishing between the die. It means a 2 and a 3, and a 3 and a 2 are counted separately. Like the fact whether dice 1 is 2 or 3 matters.
So then it's 4 out of 32.
Really?
Oh.
The sum of the two.
Yeah, you can have a 2, a 3, 4.
2 and 3, that's 1.
One
What?
and four.
3 and 2,
4, 1 and 4.
1 and 4,
4 and 1.
and 4 and 1.
So,
Okay? Give me a systematic way to do that. What if I ask you 8? Are you going to sort of... you have a 2 and a... How do you guess about 8? Or something else? Give me a systematic way to do that. A very popular method with dice, which any question that has dice in it, I probably recommend that you do something like this. Give me a systematic way to know how you got 4 out of 36 for that probability. Into a diagram. So here's the diagram. There's die 1 and there's die 2. And now we're going to list all possibilities for each. So for dice 1, it can be a 1, or a 2, or a 3, or a 4, or a 5, or a 6. For die 2, it can also be a 1, or a 2, or a 3, or a 4, or a 5, or a 6. Now let's say I'm using this table to give me the sum, right? Which I could ask you other things. I could ask you, what about the difference? What about the product? What about this, right? You can make a table for that. So here if I'm looking at the sum of the dice, what am I going to get? Well, in this situation, if dice 1 is a 1 and this is a 1, the sum is 2, right? And I can go through and I can fill these up. So this would be 3, 4, 5, 6, 7. 3, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9, 10. 6, 7, 8, 9, 10, 11. 7, 8, 9, 10, 11, 12. Right? So those are all possible outcomes for the sum. And I can figure them out by drawing that diagram. Now, when you have that table drawn, it's sort of easy to see what the total possibilities are. It's just a 6 by 6 grid. The total possibilities is 6 by 6. So that's 36. Now if I ask you how many ways are there to get a 5, you count the number of ways to get a 5. That's your K from the equally likelihood principle, right? So there are 4 ways to get a 5. So this means that for B, the probability of getting the sum of 5 is going to be 4 out of 36. And when I look at it this way, I can ask you the sum of anything. What's the sum of an 8? You're probably getting an 8. Well, it's 1, 2, 3, 4, 5. 5 out of 36. Or you can just see it right away. C, if you were to bet what the sum would be, what would you bet it is?
7.
Why is 7?
It's the most likely.
It's the most likely. It's the highest number, right? The 7 goes along the main diagonal. There are 1, 2, 3, 4, 5, 6. Right? That's the most. That's the guy with the most possible outcomes.
No.
What?
6
You're
also has.
counting the
No,
die
6 has
number.
5.
You accidentally counted the die.
Don't count this. These are the. This is not a part of the table. Right? These are the possibilities for this guy. And you don't count the top. The sum is on the inside here. Right? 7 is the guy that shows up most often. From the table, 7 is most likely. Bet on 7. So if you had to bet on this game, someone's rolling 2 dice and you have to say what number you think it's going to be, you should pick 7. Right? That's the one that gives you the most chance of winning.
But if you're presented with this situation,
Yeah.
like,
Means your life went wrong, right? Should have stayed in school. If you have this situation, you probably
If you have the
You have to-
situation, like you're really gonna,
Find better.
they want an answer right away, right? Like, are you gonna do the chart quickly and place
You
your
just
bet?
hold up, give me a notebook.
Or are you just showing us the science behind it?
No, you say, let me think about it. And then go to the bathroom.
That's what I
Whoa. It'd be like a beautiful mind writing on the mirrors. Equation in your head.
So we have to draw diagrams for this one.
Yeah, is there like another?
Yeah, like Charlie, you think in your head, well, I can get a 2 and a 3 or the. But that'll actually take longer, I think.
Have you seen the bar scene from A Beautiful Mind?
Of course.
The bar scene from A Beautiful Mind?
Another example. How many 10-digit phone numbers are possible if the first digit must be a 1? No restriction otherwise. E. What if the second digit cannot be 0? Then how many possible phone numbers do you have? If your number has this format, what's probably that your stalker can guess your phone number?
We can't calculate that.
He's highly motivated and he's gonna sit there at the phone all day. Hello? Hello? Right? What's the probability that he'll actually get it right? Say on the first try. D.
0.
It's not 0. You're not as safe as you. What if, here's a crazy situation. What if he knows the last 7 digits
Of your phone number?
of your phone?
The last 7 digits?
He knows the last 7 digits.
Ain't that your phone number?
Yeah, he's so talented. Marry that dude.
This
He's
is
so
this is
smart
the
and
format we're
talented.
using here.
Oh, the 10 digit.
I'm so, please don't marry him.
I mean, that's pretty close. I mean.
What's the probability he can guess it? How safe are you?
Not safe at all. This disconnect your phone.
Let's change your phone number.
Just move. You're introduced.
I love how you assume only guys are killers.
There are crazy women out there.
Equal rights, right? Women can be stalkers too. You know. Sorry, okay. Such a sexist Jhevon. Let's do 8. How many possible phone numbers are there if the first digit must be a 1? Yeah? 10 billion? 10 to the 10 power? How'd you get that?
No, 10 to 9 power.
How'd you get that?
Because the first digit must be 1, right? So you have
Right, you think of it in terms of stages. Each digit is a stage, right? So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 stages, but this one is already accounted for. That has to be a 1. Assuming no other restrictions, it means that the digits that can show up here can be any other digit, right? So you have here, you have 9 possibilities, 10 possibilities, including 0. 10 possibilities, 10 possibilities, 10 possibilities, 10 possibilities, 10 possibilities, 10 possibilities, 10 possibilities. So the multiplication rule says there are 10 to the 9 possible numbers. Right? By multiplication. Right? So there are a billion possible phone numbers with this. Yeah.
If you said that the first number can either be a 4 or a 1, would it be?
Either be a 4 or a 1?
Yeah.
You'd add them. You put a 1 here, you'd have this, plus a 4 here, and that. That's actually in a later chapter. We'll do that. So if you don't know that yet, we'll get to it. Yeah, so what if we put another restriction? The second digit cannot be a 0.
So then you have 10 times 9 times 10 times 10 times 10.
You have a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But this can only have 9 choices.
Yeah.
Right? And then the rest don't matter. 10, 10, 10, 10, 10. So what do we have? 9 times 10 to the 8.
Yeah.
So we still have that first situation.
Yeah. Okay, if you have a number like this, so what's the probability of your software guessing your number? How many phone numbers do you have? Are you hiding from people?
No.
You have one number, right? And these are the total possibilities.
There's 1 out of.
While you're guessing correctly,
900.
it's not 0, but it's pretty close to 0. It's going to be 1 out of 9 times 10 to the 8, which is pretty close to a billion. Which means, let's say you have the most unlucky stalker in the world, and your phone number is the very last phone number he guesses, and he guesses a phone number every second. It'll take him 32 years to figure out your phone number. That's a long time. Every second is just 32 years. That's a lot of phone numbers. So you're pretty safe. Unless he's a super lucky stalker and he gets on the first try. Then you're not so much. Nothing is guaranteed. These are all just chances, likelihood. What if they know the last 7 digits?
It'll be 3, 10 to the 3rd, 10 7.
So we have 1, 2, 3, 4, 5, 6, 7. So D. So then he only has to guess what? 90 numbers. This means probably guessing correctly in that situation is 1 out of 90. Which is a small price to pay to live happily ever after. We were soulmates. I only dialed 90 numbers.
Wait, Jhevon, one question.
Yeah.
If he knows.
I have no experience with anything.
Okay. No, if he knows the last 7 digits, right?
Yeah.
So then we would just change, like, in the first 10 thing that you did, the multiplication rule, wouldn't you just change the last 7 digits to 1, and then it'd be 10 more chances for the first 3 digits?
No, I'm still assuming that the conditions I made before
Oh,
still
so
hold.
it's still 1 and it's
Yeah, I'm
not.
pretending
And then-
that there still has to be a 1 in the
So it
first,
only
the second
needs to know
can't be.
one number.
Yeah.
Oh, okay. This is why it's not easy.
Yeah, which usually, if I want to drop a restriction that I made before, I'll tell you in the problem. Say, pretend we're starting from a clean slate and blah, blah, blah.
Oh, so everything's still
Yeah, so everything continues to hold. If it didn't, I would have mentioned it.
This stalker needs Twitter or Instagram.
See, Alba knows how to do it.
No, it would just make
She
his life
knows how
so
to do
much
it.
easier. Like phone numbers.
They probably already have you on Instagram or Facebook.
They just want to know.
Actually, it's pretty true.
They're gonna move next door to you. I'm guessing apartments. That would be fun.
Why are we thinking about how to stop people?
Everybody's stalkers still come out. Everybody's got tips and tricks
Yeah.
for the trade.
Like what I do, right?
So in order to be the best stalker, you gotta take a stats class.
Go take a stats class. You're like, yeah, I'm definitely not gonna do that strategy. That'll take forever. Like now I know I gotta do something. I'm not gonna take 32 years to find you. Okay, some more rules. We love rules. To keep us safe. There's one, the 0 to 1 principle. The 0-1 principle. I kind of mentioned this before, but let's make it specific. The probability of any event occurring is between 0 and 1, inclusive. Getting a number outside this range is a minor blasphemy, so if you get a probability that's not in this range, don't write it down. Write down Mary had a little lamb or whatever, so you don't get a 0 for the whole thing. Probability of an impossible event. Is 0, right? That's how you attain these endpoints. These are extremes. An impossible event, the probability is 0. Probability of a certain event. That's how you get a 1. If you know it's certain. The sun will come out tomorrow.
You forgot the T in it.
What?
The probability of any event. That's an even.
There's a T right there. It's right there. Okay, here's another one. The sum of all possible, the sum of all probabilities is 1. So if you find the probability of there are a bunch of possible outcomes, and you find the probability of each of them, and they're all less than 1, which is fine. But then when you add them all up, you get something bigger than 1, something's wrong, right? All possibilities, that has probability 1, because all possibilities is a certain event. It's certain to be one of these things. We don't know which, but it's definitely one of them. So if I add up all probabilities, I should get 1 as the answer. Okay, let's do it. Expanding on the third. It's a super useful rule. We'll use it all the time. You get the what's called rule of complements. I'll tell you what the rule of complements is. an event let A with a little c up here denotes a complement which I usually say a complement or the complement of A. Note that A complement is the event that A does not occur. Right? So A is the event the sun will come out tomorrow. A complement would be the event the sun doesn't come out tomorrow, which would be bad. So A complement is what we say it does not occur. What are the chances of something not occurring? Right? We call that the complement probability. So P of A is probability of A. And if I take the probability of a complement, this is the complement probability of A. Which is probably that A does not occur. So now you think about it, for a given event, what are the possibilities between occurrences? It can either occur or not. There are only two possible cases. So the total possible cases, there are only two for a given event in terms of occurrence. And so that means if I add the probability of an event happening and I plus probability of it not happening, that's a certain event. It either will happen or it won't happen. So if I add them, the answer should be 1. This is called the rule of complements. A lot of the times it's what you do is you solve for P of A complement and you write it in this form. This is 1 minus probability of A. Sometimes, a lot of the times, we will think of it in this way. Probability of what you want is 1 minus probability of what you don't want. And vice versa. Right. This can greatly help us to reduce the amount of computations we want to worry about. So here's one situation where the rule of complements comes in handy. Going back to another previous example, we toss a fair coin 3 times. What is the probability of getting at least one parenthetical statement? By the way, phrases are used often. At least. What does it mean mathematically?
More than. Oh, mathematically.
Greater than or equal to. That's how you think of it. Right? Greater than or equal to. Another phrase that you'll see often is at most, which just means less than or equal to. Right? So just that. So when I say the probability of getting at least 1 heads, I mean get 1 heads or more. You get 1 heads or 2 heads or 3 heads or 4 heads or 5 heads. All those possibilities. What is the probability of that? Right, now this one's not so bad. We kind of set up the diagrams for it and everything already. But let's say we didn't do all that and we're approaching this problem from scratch. It turns out the nicer way to attack this problem is through the complement probability and not through just a direct brute force way of doing it, right? Because now it's at least one head, so there are many possibilities. What if you get one, right? And that's going to have many implications, right? You could get the head on the first one, but not on the second or the third, right? Or you could get a head on the first, on the second, but not on those. Or you could get this. And that's just how many ways you can get one of them. And then you have to think, what if I have two? And now you have to set that up and you have to think about that situation, right? So brute forcing it, it's going to take some time. But think of it this way. What's the opposite of getting at least one head?
Not getting.
Right? Meaning, what's the opposite of getting one or more?
Not getting any.
Not getting any at all. None. And how many ways can that happen?
One.
Only one. I don't even have to count anything. Only one way for this to happen. Right? Meaning, you get all tails. Right? So I could go through and figure out how many ways can I get at least one heads, and I have to be counting the probability. What if I get on the first toss, or the second, or the third, and this and that, and you have to rearrange these things. But if you think in terms of the opposite, what you don't want to happen, there's only one way for that to occur. So now you can actually use that to your benefit. So then you'd say something like the probability of at least one is the complement. Probably of what we want is 1 minus the probability of what we don't want. And how many ways are there to get none? Right? This is just 1 minus the probability of all tails. Right? Now remember we know that there are 8 possible outcomes, right? That was 8. So how many ways are there to get all tails? Literally only one. You flip a tail, then a tail, then a tail. So probably 7 over 8. So there are times when what you want is kind of complicated to get to, but if you look at it from the flip side, the opposite is actually easier. And when that occurs, this guy is going to be your best friend. And that's going to occur all the time. Very often occurs, right? So you can use the rule of complements. So this is something you want to know. Sometimes it's easier to not get what you want, like enough sleep. So that's a trick issue, I would say. I'll leave you with this, which we'll pick up with next time, and then we'll just end. Think about this. Actually think about it. Don't be like, forget about it. Then next class you go, did you think about it? Think about what? Give something to your normal. Yeah. 10 people at a party. Very small party. It's a math party.
Yeah.
A soiree.
Party.
That's why nobody went to that party. Somebody described it as soiree.
Yeah, you want to come to my soiree? Only 10 people showed up. Only 10 people understood what that was. What was a soiree? I want to go to your soiree.
It's like a fancy people party. Yeah, I think so.
What's the probability that at least 2 share the same birthday?
I watched the video on
Out of 10 people. It's gonna be higher than you think. In this class, you know how likely it is for two of you to have the same birthday?
Same year as well.
No, not the
No,
same
this
year.
day.
The month and the date. Month, date. What is the probability at least one person has your birthday?
I was born on February 29th. No, I'm kidding. Oh, God forbid. That's the saddest birthday.
That's the kind of thing that makes you get a stalker. Like, I was also born on February 29th. I've never met anyone like this. We're meant for each other. I'm like, get away from me, freak, and goes home.
You gotta find
We're meant for each other, don't you understand? I didn't go to Jhevon's class. I should have used Twitter, Facebook, or something. Yeah, assuming you're one of the 10. So you're one of the people who knows what a soiree is because you're pretentious. And you actually show up to this party. What's the probability that someone else has your birthday? Next time we'll talk about and and or. And then that will finish up chapter 10 and then or. The next test is what? After chapter 11?
Yeah.
Okay. So.
Like,
How about that quiz? What is that?
Quiz right now?
No, there's only like 4 minutes left.
Why
No,
would
you're
you-
gonna stop.
So next test is probably in 2 weeks.
on a Monday?
Probably on the Wednesday.
Okay.
Probably.
So like right before, the break?
Yeah, Wednesday after next is probably. I should finish chapter 11 by Wednesday next week.
Right before the break.